Hello and welcome to today's video. This is two of two videos looking at optimization using Design Studio. In the first example, we looked at a simply supported steel structure and we worked out what the stiffness to weight ratio of that was when it was subjected to a UDL. We then showed that actually this stiffness to weight ratio was much the same when using carbon fibre reinforced plastic if the part was arbitrarily laid up. We then went on to use Design Studio to optimise the structure. We talked about variables, objectives, constraints, and we then said, okay, well, let's now optimise the structure. And we showed that the stiffness to weight ratio was significantly improved if you were laying that up using optimization techniques rather than arbitrarily laying it up. However, what we did not use was any sort of manufacturing constraints. We came up with a structure which had a theoretical number of plies in each orientation. However, they were not whole numbers, they were not discrete variables. So that's what today is going to be looking at. We're going to take the baseline, the theoretical optimized structure, which may have, I don't know, 1.5 or 2.5 plies in a certain orientation, and say, actually, we need to make those variables discrete numbers. We can have 1 ply or 2 plies or 3 plies in a certain orientation. We can't have 1.5 plies. So we're going to force Design Studio to choose from those discrete variables. So here's our structure. Just to remind us, if we look at the loading on that structure, if we go to load case, we've got one load case. We're constraining it at one end so that it can 1, 2, 3, 4, 5. There's 5 constraints there, so that can only rotate around that axis there. At this end, we're allowing it to rotate around that axis there. We're also allowing it to translate lengthways. And you can see we've got our uniformly distributed load on top of our structure. Our deformed shape looks something like, let's go to the baseline, let's clear those. There's our deformed shape, and let's animate that. So there's our structure. That's what we'd expect. Okay. And as we saw last time with our arbitrarily laid up composite structure, the maximum displacement in the middle here you can see is 5.8 millimeters. Okay. We then optimize that structure. So when we go to design cycle 13, we go to design cycle 13 displacement 1.9 millimeters. Okay, so it's now displacing by 1.9 millimeters, which is the same as our steel structure. Hence, this had the same stiffness to weight ratio. We've got the same force, we've got the same displacement, so therefore we can work out the same stiffness. But our stiffness to weight ratio is significantly improved because obviously this thing is much lighter. Okay. However, what we also saw was our variables, and if we have a look at that history file, remember our history file is just a text file. It shows us our objective. Remember, our objective was to minimize mass. So this is the mass of the structure. It started off at 29 grams. However, it was violating the constraint. It was displacing by too much. And you can see initially we set all of our layers. Remember, our layers, not our plies. So our layers are 1 mil thick. Each ply is 0.2 millimeters. So therefore, we're suggesting that there are 5 plies in each layer, i.e. this thing is 25 plies thick. However, when we get to the last cycle, we're no longer violating the constraint. We're meeting the displacement of 1.9 millimeters. Our objective has gone down significantly. So we've gone back down to, well, before we were at 29 grams there, now we're at 30 grams. So our mass has gone up slightly, but we're not violating the constraint. But when you look at the layer thicknesses, we can see that those are quite theoretical. If we take those numbers and divide them by 0.2 millimeters, we can see the number of plies that we would have in each orientation. So if we take that first layer, let's have a look at that. So that is 2.5. Let me just get my calculator out. 2.51991 times 10 to the minus 4. And if we divide that by 0.2, it's 10 to the minus 3, because that's the thickness of each ply, that suggests that we've got 1.2599705 plies at that orientation. And remember, that was our minus 90 layer. Minus 90, minus 45, 0, 45, 90. So that suggests that we've got just over 1 1/4 plies at minus 90 degrees. Clearly, we're not able to manufacture that. We can have 1 ply or we can have 2 plies. We can't have 1 1/4 plies. Okay, so this structure theoretically meets the displacement constraint. It's much lighter, our stiffness to weight ratio is much better, however we cannot manufacture the thing. So what we need to do now is we need to change our variables to make them discrete variables so that we can choose from 0.2 millimeters, 0.4 millimeters, 0.6 millimeters, 0.8 millimeters, or 1 millimeter, i.e. we can say we could have 1 ply or 2 plies or 3 plies or 4 plies, etc. But we can't have this this number here, just over 1 1/4 ply, 1 1/4 plies. Clearly we're not able to manufacture that. Okay, so what we're going to have to do now, like I say, is go in and change our variables from those real numbers to discrete numbers. Okay, so if we go into our variables, so if we go into design and choose variables from this drop down list, so design variables, we can see we set up 5 design variables, 1 for each layer, and then we link those to those layers so that we could design our structure. If we look at those design variables, if we click on modify, the first one you can see is an independent design variable, and that's what Design Studio calls our design variables when they are real numbers. If we click on next and examine that, we can see we had an initial value of 1, a lower bound of 0.2 millimeters, and an upper bound of 3 millimeters. So what we said was initially it's 1 mil, that layer, but it can go down to 0.2 millimeters, 1 ply, or it can go up to 3 millimeters, 15 plies. And it can have any number between those 2 limits. Okay, and that's why we came up with that value of 1 1/4 ply. For that variable. It's theoretically possible, or it is possible between the limits that we've set, but it's not manufacturable. So what we need to do now is we need to, if we cancel that, if we look at those design variables, if we click on that first one and we go to modify, instead of it being an independent design variable, let's make it a discrete design variable. So we click on that radio button there, discrete design variable. Click on next, and then it's asking us, okay, initial value. If we look at what I've asked you to do, first discrete value. Okay, so we're saying it can be 0.2, 0.4, 0.6, 0.8, and so on, all the way through to 3 mil. So our first discrete value is going to be 0.2 millimeters, so that's the minimum it can be. And then we're going to add all of our increments, 0.2 millimeter increments, up to this limit here. And we're going to say, okay, it can choose any of those values. So let's do that. So our initial value was 1 mil. Our lower bound was 0.2 mil. And our upper bound is 3 mil. So our first discrete value would be 0.2 times 10 to the minus 3, 0.2 millimeters. And our increment then would be 1 ply. So we start off with 1 ply and we increment by 1 ply, 0.2 times 10 to the minus 3. And then number of additional values, if we click that to 14, and click on generate and add values, we can see down here the discrete values that we're allowing Design Studio to choose from. If we click on generate and add values, so it takes our initial values. Let's get rid of that first one. Our initial value of 0.2 millimeters, so that's 1 ply, 2 ply, 3 ply, 4 ply, 5 plies, all the way through to 3 mil. See, so you can see we've got those discrete values that Design Studio can choose from. Okay, then we click on finish. So that's that first one. Let's just repeat that. So we'll change that to discrete. Our initial value was 0.2 millimeters. Our increment was 0.2 millimeters. Our number of values was 14. Generate and add values. Move that first one, 0.2, all the way to 3 mil. Finish. Okay, repeat that again. Discrete. 0.2, 14. Generate, add values. Remove the first one. Finish. Next one. 2.2, 14. Generate, remove the first one. Finish. And then finally the last one. So you can see these are all being changed from discrete, from independent design variables to discrete design variables. Let's modify that last one, make it discrete. And our initial value is our first discrete value is 0.2. Our increment is 0.2. 14 additional values. Remove that first one. Click on finish. Okay. So now, if we go to Genesis Optimise, we should see a significant difference. Okay. So you can see what's happening there now. So we start off here at 29 grams. We've added mass, just like we did last time, to get the constraint violation down, and then we get our mass down up until design cycle 11 here. Look, design cycle 11, and then Design Studio says, "Oh, hang on a minute, I can't have those values that I've come up with. I'm going to have to increment or go from those values to a whole number of plies, so therefore I've got to throw mass at the structure." So it's not quite as efficient as it was. The mass has gone up, but now we can actually manufacture the thing. Okay, so let's now open that history file and examine that. So if we look in where we've just been running that, 207, it's that one there, we open that. Okay, so this is the history file, exactly as we were looking at it before. So we start off with 1 mil in each layer. We're violating our constraint. Our mass is 29 grams. If we get down to this cycle here, we're at 30 grams now. We're not violating the constraint, and we've got this strange number of thickness or a strange number of plies in each layer. These aren't discrete values. But then when we go from design cycle 11 to design cycle 12, we can see the mass has gone up. We've gone from 30 grams up to 33.5 grams. So we've added 3.5 grams. We're not violating the constraint, but now we can see we've got something which is manufacturable. So this is 0.4 millimeters in this orientation. This is 1 millimeter in this orientation, 3 millimeters in this orientation, 1 millimeter in this orientation, and 0.4 millimeters in this orientation. So you can see, that tells us how we go about laying that up. We've got this manufacturable, our manufacturing suggestion, therefore, would be 2 plies at -90, 5 plies at -45, 15 plies at 0 degrees, 5 plies at 45, and 2 plies at 90 degrees. Okay, so let's have a look at the results in this PDF. which summarises what we've just looked at. So notice this job here is slightly different. It's been run at a slightly different time, but we've got essentially the same thing. We've got our layers minus 90, minus 45, 0, 45, 90. In this particular run, you can see what that's suggesting is 2 plies at minus 90, 0.4, 5 plies at minus 45, 1 mil, 15 plies at 3 millimeters, and actually we've now got 4 plies at 45 degrees, 0.8 millimeters, and then 2 plies at 90 degrees minus 0.4 millimeters. So that gives us a total of 28 plies. If each ply is 0.2 millimeters, that gives us a thickness of 5.6 millimeters. So we've got our layup. We can understand our stiffness. Our stiffness is going to be the same as our steel structure. We've got the same force, we've got the same displacement, because that's what we have asked it to do. We can now examine the history file, and remember this is our mass, 33 grams, so therefore we can work out our weight, so therefore we can get our stiffness to weight ratio. So let's do that. If we summarize our runs, which is what this PDF has done here, there we go. You can see our steel baseline was 3 millimeters thick, had a deflection of 1.9 millimeters, was 97 grams, load was 500 newtons, therefore our stiffness is 263 newtons per millimeter, and our stiffness to weight ratio therefore is 308 newtons squared per millimeter. Our composite baseline, it was 5 mil thick, each layer was 1 mil. So therefore there was 5 mil thick in total. There was 25 plies. Our deflection was 5.8 millimeters. Our mass was 29 grams, 500 newtons. Our stiffness is much lower because it's deflected by 5.8 mil instead of 1.9 mil. So our stiffness to weight ratio actually is about the same, 297 newtons squared per millimeter. And then our optimised structure, which we saw at the end of the last video, was 5.2 millimeters. We made it a little bit thicker, but we had got our deflection right down to 1.9 millimeters. Remember, that was our constraint. We had therefore met that constraint. Our mass was 30 grams, so we'd added a little bit of mass to get our deflection right down. Our stiffness now is the same. So therefore our stiffness to weight ratio is significantly better. It's nearly 3 times as good. Look, 894 newtons squared per millimeter. Remember, these are strange units. Don't worry too much about the units. It's the number that I'm interested in. Okay, so this number here is about the same. It's about 300. This number here is about 900. It's nearly 3 times as much. What we've done today now is we have optimized the structure using discrete design variables. Okay, now in order to do that, we've added a little bit more mass. We've gone up to 32, 33 grams, I think, in the example we've shown today. Our deflection is still exactly the same, but now we can actually manufacture this part. So our stiffness is the same still. Our mass has gone up slightly, so therefore our stiffness to weight ratio has come down slightly, but it's still significantly better than it was. Okay, so before we were 308 newtons squared per millimeter for the baseline steel part. Now we've got a composite structure which we can actually manufacture, and we know the suggested layup of that structure. We've got it there. Look, there's our suggested layup of that structure, and we know that will give us the same stiffness as the steel part, but the weight is significantly less. We've gone down from 97 grams down to 32 grams, so our stiffness to weight ratio is much better. So what we've done there today is we have looked at our theoretical optimized composite structure. We've changed our variables from real numbers to discrete numbers. We've re-optimized it, and by doing that we've added a little bit of mass, but we can actually manufacture the part now, and the stiffness to weight ratio has gone down slightly, but it's still significantly better than it was with the initial baseline part. Okay, so if you've got any questions on that, let me know. We'll have plenty of time to go through those examples in class, and you should therefore be able to optimize a composite structure within Design Studio. Okay, until next time, cheers, bye bye.